Hello again. This is our last video on linear transformations. In this video, we're going to talk about one-to-one and onto transformation. So let's start with one-to-one. Here's the definition. If you have a mapping T, it's said to be one-to-one. By the way, T goes from Rn to Rm. So it's said to be one-to-one if for each B in Rm is the image of at most one X in Rn. So we start with a B, that's the image, so it's in the range, in the Rm. And if there is more than one point going to that, that's in the domain, it's not one-to-one. Here's a nice picture there where you can see here if each image has just at most one point, it is one-to-one. So let's start with functions. I have an example down here. Back in our algebra days, is f, or pre-calculus, if f goes from just r to r, is f one-to-one if f of x is x squared? Well, the answer is no. So let's look at the definition. So I'm going to let b equal 4 so that f of x equals 4. So b is going to be in my range. So that means that x squared equals 4, or x equals plus or minus 2. There's more than one, so it's not one-to-one. Versus e to the x. E to the x is one-to-one. So I'm going to do the same thing. I don't have a value to do, so this time I'm going to let, since it is one-to-one, I'm going to just let b in the range where f of b, or f of x, is equal to b. So what does this mean? This means f of x was e, so e to the x is equal to b. And I can solve for x, or if I solve for x, actually I could take the ln of both sides, can I? And this would be x is equal to ln of b. X has a single value. If, by the way, if b is bigger than 0, then there is one solution. I realize if b is less than 0, there's no solution. That would be something that would be in the codomain but not in the range. That's okay. So for each b that's, it says here, it talks about that, is in the image, right? For each b that is in the image. So that one just would not be in the image. So it is one-to-one. So let's go ahead and graph these. The graph of the first one is just a parabola. And you can see when we pick 4, let's call this 4, there's 2 values. Not good. If you remember from pre-calculus, there was something called a horizontal line test to show if it was one-to-one. If you remember, the vertical line test showed it was a function, and a horizontal line test shows it's one-to-one. E to the x looks something like this, and you can see where it satisfies both the horizontal and the vertical line tests. Now let's work with our transformations. We have a theorem. Let's talk about our theorem next. Theorem 11. So if we have a linear transformation, it turns out that T is one-to-one if and only if the homogeneous equation T of x equals 0 only has the trivial solution. They have the proof in the book that let's just quickly go over. What they're doing here is showing that if and only if means P if and only if Q. And so the first part they're going to show P implies Q. and this is going to be our P, and that's going to be our Q. So if T is 1 to 1, that is the P. And it says since T is linear, we know T of 0 equals 0. Okay, so then the equation, since it is 1 to 1, it only has one solution, hence only the trivial solution. Then the next part, they do Q implies P. And this is a little bit harder, but what they do here is they assume, instead of doing this one, they're going to do not P implies not Q. If you have had anything about logic, this is the same equivalent statement as this. So that's why they said, let's assume it's not 1 to 1. Therefore, B has at least two different images, say U and V, and then they state that here more formally. And then they look at T of U minus V, which because this is linear, you can write it like this, which is B minus B, which is equal to 0. But we just said that it is not 1 to 1, so U was not equal to V. Therefore, we had a contradiction. Oops. Not Q. So, therefore, Q implies P. Let's look at an example of this. Example 4. So let T be the linear transformation whose standard matrix is this matrix A. We want to see if T is 1 to 1. So we know T of X usually is AX. And in this case, it would be, we want to see, well, we can write that out. But what we really want to do, if you go back here, we know, we can erase these now, we know that if we have only the trivial solution, it's 1 to 1. So I'm going to look at this. So we're just going to look at the equation or the matrix, because AX equals 0. There it is. And you can see here's a pivot, here's a pivot, here's a pivot. Oh, that means that X3, if this is X1, this is X2, X3 is free. Oops, let's call that 4. So we know that X3 is free when X free is, when there's a variable that is free, that means that there is more than one answer. So therefore each B is the image of more than one X. That is, T is not 1 to 1. Onto. To see if T maps R4 onto R3, we need the definition. So let's do that next. The definition. Here's the definition of onto. A mapping T from Rn to Rm is said to be onto Rm, onto Rm, the codomain there, if each B in Rm is the image of at least one X in Rn. They have a great picture here, something that is not onto and something that's onto. So in other words, if the range is, right, not the whole thing, kind of like spanning, right? So for each B in Rm, right, there's a bunch of images in Rm that one of the X's does not get to. That, right, is not onto. But if the whole range is the same as the codomain, then it's said to be onto, which is why we have the next theorem. So here it turns out that if T is a linear transformation from Rn to Rm, and A is the standard matrix for T, then T maps Rn onto Rm if and only if, right, the columns of A, there it is, span Rm. And then they also have another one for one-to-one, T is also one-to-one. We can look at that one as well. If, by the way, if the columns of A are linearly independent. The first one, these have been all proven before, so we really do not need to prove these again. It's just another way of stating Theorem 4 and 1.4. If you go back and look at that. It said that the columns of A span Rm if and only if for each B in Rm the equation is consistent, which is the same thing we have here, because in other words, if and only if every B, the equation T of x equal B has at least one solution, which is exactly the definition. And by the way, the linearly independent comes from the definitions that we saw in 1.7. The equation T of x equals 0 and x equals 0 are the same, right? So by theorem 11, we know the one before, we just saw T is 1-to-1 if and only if ax equals 0 only has a trivial solution. But from 1.7, we know that this happens if and only if the columns of A are linearly independent. So it's all connected. Let's look at back to example 4, and see if we can figure out if T is onto. So I want to check out whether, to see if it's onto, if the columns of A just span Rm. So if you remember how we did that, we looked at B in the codomain. And let's look at T of x equals B, and it's the same as what matrix? And the A here with a B1, B2, B3. And again, here's a pivot, here's a pivot, here's a pivot. This is consistent for all B. So the span of these columns, I'm just going to call them the columns of A, we're going to see that later, is going to be all B. So just R3. So yes, T maps R4 onto R3. Let's look at example 5, our last example. So let T be defined as such. We're going to show that T is 1-to-1, and does T map R2 into R3. It is R2 because the domain is R2, and there's the codomain. You can see there's 3 entries there. That is R3. So I'm going to do the onto first. Here's the solution to example 5. So I'm going to let B be in R3. The same thing. So T of x equals B. I just rewrote T of x in a matrix form. And with the B1, B2, B3, I want to solve this. I want to show that B1 and B2, B3 are consistent for all B3. But I went and I interchanged row 1 and row 3 there. And then I got the zeros using these rules right here. And then I realized I get a -8 there. And then when I multiply the second row by -1, add the third, I get the zeros with this. If you actually go and do that out, it's not consistent for all B. There's some B that it works, some B that it doesn't, but it's not consistent, so it's not onto. What about 1-to-1? To show T is 1-to-1, we need to show T of x equals 0 only has this trivial solution. So I just put zeros here, which means I would just have zeros there. So I would have, all the steps would be the same, but this last column would be zeros, and I only have 2 pivots. It only has a trivial solution, so it is 1 to